ABC Calc.
Aaron here.
This is a banana. More specifically, a Cavendish banana, which is one of over 1,000 different types of bananas. But what makes a banana a banana? We as a species put things into groups based on their common characteristics. Bananas all grow in tropical climates. They all have stems, peels, and look a little bit like a telephone. But they can be distinguished from each other based on their color, shape, and size, allowing one to create subsets of banana groups. A group can be defined as a collection of things. Another group can be defined as apples, or all oranges, or all non-oranges.
This is the groundwork for naive set theory, developed in the latter half of the 19th century by Georg Cantor. In naive set theory, a set is loosely defined as a collection of things. This vague definition allowed flexibility within sets, as sets could now be applied to a broad range of topics. For example, within set theory, you could have a set of all of the traffic cones in the universe. You could also have the set of all integers, or all of the prime numbers, or all of the perfect squares. Naive set theory allowed sets to be placed within sets. An example of this would be the collection and division of real numbers. Real numbers are split into subsets of rational and irrational numbers. Rational numbers are then further subdivided into integers. Integers are subdivided into whole numbers, and whole numbers are subdivided into natural numbers. In this example, natural numbers are a subset of whole numbers are a subset of integers, and so on.
The basis of set theory was created using several axioms, or postulates. An axiom is an unprovable rule or principle that is true because it is self-evident or particularly useful. For example, the reflexive axiom asserts that A equals A. Likewise, the symmetric axiom states that A equals B, so B equals A. These axioms are both based on Euclid's common notion 1. Things are equal to the same thing are equal to each other. These facts may seem blatantly obvious, but this is the nature of axioms. They cement the truth so that they can be applied in higher mathematics. Mathematicians developed a special language for set theory to efficiently communicate the tedious instructions associated with the various axioms and theorems. Consider the following expression. This is called set builder notation, but don't be intimidated by the unusual symbols. This simply means that the set of all x's where x is greater than 0. One could also write this list as each individual member by saying 1, 2, 3, 4, 5, and so on, all the way to infinity, but this would take a while. Set builder notation is a productive way of describing a set by the common properties of its members rather than by the contents themselves.
The common property or rule established is known as the logical predicate. All values of x for which the predicate holds true are members of the set being defined. The domain of a set is a range of all the values of x that belong to a particular third set, Z. While indicating a writing of x using the predicate, the domain of a set can also be adjoined with the predicate by writing this. This expression translates to the set of all x such that x is an element of or a member of Z, and phi of x, the predicate, is true.
A set is sometimes preceded by a group of quantifiers, the quantity of specimens in the domain of interest. Existential quantification, denoted by this symbol, translates to there exists, there is at least one, or for some. Essentially, they predicate the property for at least one member of the domain. Universal quantification, denoted by this symbol, translates to for all or given any, predicating the property for every member of the domain. Take the expression which states that for all x's there exists Z where x is an element of Z.
Now, let's take a step back from all of this notation and imagine this hypothetical situation. Imagine a barber that shaves all those and only those who do not shave themselves. Does this barber shave himself? If we take the initial condition that he doesn't shave himself, he by definition doesn't shave himself, meaning he is part of the group that he has to shave, meaning he does shave himself. Conversely, if we take the initial condition that he does shave himself, then he doesn't shave those and only those who do not shave themselves, meaning he would cease to be a barber and could not shave himself. In simpler terms, if he shaves himself, he doesn't, and if he doesn't shave himself, he does. Paradox. The situation is called the barber's paradox, which is a variation of Russell's paradox.
In order to understand Russell's paradox in terms of set theory, let us define a set as normal if the set is not a member of itself, and abnormal if the set is a member of itself. Now let's take set A, where A is all the squares in a plane. A itself is not a member or not a square in the plane, so it's not a member of itself and therefore is normal. Now let's take set B, where B is all the non-squares in the plane. B is then a member of itself because it is not a square in the plane. Therefore, B is abnormal.
Let R be the set of all sets that do not contain themselves. Russell's paradox poses the question, does R contain itself? If R contains itself, then R must be a set that is not a member of itself by definition R, which is contradictory. If R doesn't contain itself, then R is a set that does not contain itself, so it should be contained in the set R, which is also contradictory. Russell's paradox looks like this in set notation, which in plain language means that R is a set of all x's where x is not an element of x. Therefore, R is an element of R, and R is also not an element of R, which is paradoxical. This is an incredibly important paradox because it shows that naive set theory, the theory onto which all other mathematics is built off of, is inconsistent. Once this paradox was unearthed, mathematics as a whole could have been inconsistent.
At this point, Russell wrote to fellow mathematician Gottlob Frege. Both Russell and Frege are considered to be the founders of analytical philosophy. Analytical philosophy is a branch of philosophy that uses logic and systematic procedures to better understand the world. As a result, both were invested in set theory because it offered a way of classifying and organizing and cataloging the world around them. Prior to the discovery of the paradox, Frege had published Foundations of Mathematics. Unfortunately, Frege relied on the axioms found in naive set theory to lay his foundation. Russell's paradox illustrated that these axioms were not consistent until changes to the axioms of the set theory were made. The foundations of mathematics as a whole were cracked.
Just like this mattress.
The aftermath of Russell's paradox brought about a reassessment of the vague properties defined by naive set theory. Mathematicians Ernst Zermelo and Abraham Frankel introduced their axiomatic system, Zermelo-Frankel set theory, in 1908. An axiomatic system is a set of axioms from which all axioms can be used in conjunction to logically derive theorems. A system must be consistent, meaning it lacks contradiction, independent, so theorems can't be derived from multiple axioms, and complete, so that every statement is derivable.
Zermelo-Frankel set theory is often abbreviated as ZFC, where ZF stands for Zermelo and Frankel, as you'd expect, and the D stands for the axiom of choice. The axiom of choice is regarded as separate from the others because it has controversy surrounding it regarding the completeness of the axiom raised by the ideas such as the Banach-Tarski paradox. Should I do it one more time?
No.
The axioms of ZFC only refer to pure sets, which are sets whose elements are all hereditary sets, or elements of the set are themselves sets. ZFC also does not allow for the existence of a universal set, the set of all sets, nor for unrestricted comprehension, therefore avoiding Russell's paradox. Unrestricted comprehension states that for any formula phi of x containing x as a free variable, there will exist the set whose members are exactly those objects that satisfy phi of x. This is okay, I'm sorry.
Now let's take a closer look at the axioms of ZFC that debunk Russell's paradox. First off, we have the axiom of extenentiality. In plain language, this means that two sets are equal if they have the same elements. Next is the axiom of regularity, which states that for all non-empty sets S, there exists an element of S that contains no similar elements with S. This basically means that no set is an element of itself, and every set has an ordinal rank, meaning that elements can be arranged one after another.
This is the axiom schema of specification. It says that given any property of phi in set X, there exists a set containing all elements of X that satisfy phi. The axiom of pairing states that given two elements, there exists a set containing exactly those two elements. Next is the axiom of union, which states that there exists a set Y consisting of the union of all elements of X. For example, the set 1, 2 and set 2, 3 can be combined into the single set 1, 2, 3.
The axiom of schema replacement states that the set of all outputs of a function under the definable function will also fall inside a set. For example, the outputs of the function f of x will form a function. The axiom of infinity simply states that the infinite set exists.
This is the axiom of power set. In ordinary language, it means that a set Z is a subset of set X if and only if every element of Z is also an element of X. An example of this would be the natural numbers being a subset of whole numbers, as all natural numbers are also whole numbers. Finally, the axiom of choice states that one can construct a new set from a collection of sets by using an element from each set in the collection of sets.
Okay. Alright. Using these axioms, set theory has provided mathematics with a precise language for defining mathematical terms in a variety of ways. For example, set theory has created a way to define and manipulate various complete infinities, such as real numbers, and it has provided precise definitions as the foundation for many mathematical fields.
After the loosely held definitions of Cantor's naive set theory were exploited by Russell's paradox in 1901, the foundations of mathematics were transformed to remain harmonious with reality. Grouping things into sets continues to play a major role in our world, whether it's the classification of numbers or bananas. We as a species will always find more ways to clump together our surroundings to better understand them. And as always, thanks for watching.
Is that it?
Yeah, I think that's fine.
Dude, that doesn't even make any sense, man. What the? This is where we're gonna need pictures on the screen.
Do a star.
How I draw a star. Yeah, that works. And then,
Yeah, and then